Okay, to continue with the steps to be followed in order to plot the root locus. So we were discussing about the asymptotes and the angles of asymptotes. That was point number 5, correct? So asymptotes are the straight lines which are used to take the root locus to infinity. Whenever a branch goes to infinity, it has to follow what is called as an asymptote. Okay, next let's go to the step number 6 now. Here we discuss about what is called as a breakaway or break-in point. Okay, this is break away. So equivalent to break away, we will have break in also. That also coming. That will come under the same point. Okay, now we know that the root locus always starts from a pole and it is directed towards a zero. If you have a finite zero, in the sense if we can locate a zero on the graph, that is a real zero, the root locus which actually starts from a pole will be going towards that zero. If you don't have a finite zero on the graph, we can assume that the zero is present at infinity and a branch will go towards infinity by using the asymptotes. Okay, now what if there are two poles and the because of the steps we already have discussed, there may be a case wherein the two branches that originate from two different poles might come towards each other, right? This scenario we already have faced. Anyway, let's give an example now. Let's say there is a pole here, there is another pole here. Okay, this I know that now in this part there is no root locus because the condition is not satisfied. The number of zeros or sum of zeros and the poles towards the right side is an even number which is 0, so there is no root locus. Root locus exists between these two, that's for sure, correct? So that indicates that there is one branch coming from this pole to the right, one branch is actually coming from this side. So from this pole there is a branch coming towards left. Now we see that there are two branches coming towards each other, right? Which means, right, the two branches there, we don't have two zeros to compensate. So there I don't find any finite zero, which means the branches should go to infinity, right? In such case we see that somewhere at the middle, it's not necessary that it's always the midpoint of the two numbers, the locations of poles. Somewhere at the middle, right, you will get a particular point, right? You will get a point called as a breakaway point. Okay, so breakaway, it's said to be breakaway because the branches will go to infinity. From that point it's breaking out, so that's why it is breakaway, right? So at this particular point is said to be, this point is said to be the breakaway point, right? So such scenario, right, whenever the two branches come towards each other, right, somewhere at the point somewhere at the middle they will meet and break away, right? So let's define that. Let's see how to find out that point now. Okay, when two branches of the root locus whenever two different branches of root locus come towards each other, right, we get a point of meeting from which the they break it. Such point is the breakaway point. Okay, yeah. Now we'll see the other scenario, that is a break in. Right. When you have two zeros, right, we expect that the two branches that come towards the zeros, right, might come and meet at a common point between them, right? So this is a zero, this is a zero. Once again, according to the basic rules of the root locus, I expect a root locus here. So it means there have to be two branches coming to this, actually, like this, right? So somewhere at the middle, right, maybe they are coming into that, right? So from it's not necessary it has to come from infinity. Okay, maybe there are two finite zeros, sorry, two finite poles located on the graph. Whatever branch originates from there might come and meet over. Okay, so this particular point is now called as the break in point. Now, so how to find that, right? Whether the point we are going to find will be a breakaway or break in, we can simply identify by looking at whether there are zeros or poles. Okay, very simple. If two zeros, it's break in. If two poles, it's a breakaway. Okay, now to find out that, because it's present on a S plane, I have to get a S value, which is a real value. So it has to be obtained after solving the some equation, right? So the equation we can find out like this. So this is to find the break away or break in, we need to solve the dk by ds equals to 0, right? So from where we get this dk by ds, it has to be obtained from the characteristic equation. Okay, so get k equal to something, right? Get k equal to, convert the equation, characteristic equation, into this. So get k equal to something from the 1 plus gh equal to 0, which is the characteristic equation, right? Gh will be given, make 1 plus gh equal to 0. We already know that the g into h, the product will always have a k over there. Okay, so from that, get the equation for k. 1 plus gh equal to 0, the gh has a k over there. Write the equation for k, differentiate that with respect to s. Whatever you get as an answer after differentiation, right, equate that to 0 and solve. Okay, so there will be no k because k will vanish. K is what I got now. I have to perform dk by ds, and then I have to solve for the value of s. Whatever s comes, right, if you have multiple s present over there, select the s which you are expecting, right, between the range, because I am expecting like between 1 and 2. So out of the multiple s values you got, select the appropriate one which falls under that case. All right, so that's how you get the k value. Sorry, not k, the breakaway or break-in point. Fine. So once you know the breakaway or break-in point, from that point you can draw the graphs. The branches will start from there, and the branches will either go to infinity or will go to the finite zeros present on the curve, or maybe the vice versa in case of the zeros. So that is actually step number 6. Then we go for the next one, that is actually step number 7. In this, Now there is another concept to be learned. That is, let's say, I'll give an example first, then we'll look at the concept. Okay, so let's say this is the graph, and let's assume that okay, let's say this is fine. There is a zero here, there is a pole here, and let me assume there are two poles over here. Okay, so what I'm expecting here is the root locus to be present here. This is fine. Okay, and since there are no finite zeros, I'm expecting two more zeros, right? It has to go to infinity, correct? So I understand that I will definitely draw let's say asymptotes. Okay, somewhat I'll draw some asymptotes, maybe randomly I'll draw now. So let's say that the asymptotes that I'm going to get are actually uh, like like this. Maybe it's a 90-degree. Okay, asymptote in the sense, by the help of these curves, uh, it's going to reach the infinity. Okay, so this is the point at which the asymptotes start. So sigma a, and right, phi a is 90 and 270. Okay, now I have option. The option is, see, the root locus from this point, the poles can actually come like this and go to infinity, correct? It can also go from like this to infinity, correct? It's not necessary it has to come down and go. It can actually go directly from here. Another option. You see, actually, right? There are multiple options. It can start, may not be this case. Anyway, with the help of this line, it has to go to infinity. It can start here, it can go down and come like this, etc. You have multiple options, right? So I need to have a rule saying that, okay, this is the exact way how the branch should start from this pole, and it has to go to infinity or go to any other poles. So the starting of the root locus from a complex pole has to be identified by what is called as a angle of departure, right? This is a departure, right? It can actually, if the if it is say it begins like this, it's said to be 0 degrees, then it will go to infinity. Okay, it starts at it 0. Now if I say like this, it is 90 degree, because with respect to the x-axis I'm measuring the angle. Some angle needs to be measured, right? That suggests you, right, how the what is the angle of departure for a pole. Okay, so if it comes to be 180, that it starts like this and it will go to, right, it begins like this and it will, sorry, it's like this. Okay, if it is 270, it's like this. Now we get an idea that how I should draw, right? So that angle at which the root locus leaves a complex pole is called as angle of departure. Okay, the okay, I'll just write this thing. So if, maybe let's assume it starts like this, very similar to this, I should have another one like this. Okay, so it's like this. So this angle is the phi d, for phi departure, angle of departure. It will be there is a calculation to be performed, right? We have to do a calculation, then only we'll calculate, we'll get that value. Okay, so we need to calculate the angle of departure. So this is phi, I'll write DEP, phi departure. Okay, so this is actually the angle at which the root locus departs from a complex pole, right? Very similar to this, I have another equation that I am supposed to calculate with respect to the zeros. We'll write that later, but let's write the equation to be used. So the phi departure can be calculated as, this is always 180 degrees minus, so I have to take a sum here. Okay, so this is the sum of angles. uh, I can write okay, let me write in terms of angles itself. Sum of angles to the complex pole from all other, okay, I'll write the word all as well, because I need to consider every pole that is present on the graph other than this particular pole which I'm considering. Every pole, if you have three more poles, I need to calculate the angles with respect to all the three poles. Okay, so it's that term. So sum of the angles to this particular the complex pole from all other poles of the system, this is the first term. Again you subtract once again the sum of angles to the complex pole from all other zeros of the system. So in short, this is what is the actual meaning, but we'll write in this fashion. This is 180 degree minus, this is okay, there is a flower bracket outside. Okay, this it is minus sum of something minus something. So this is minus, this is sum of the angles. I write 5 poles, angle because of poles, minus the sum of the angles because of zeros. Alright, so this is the equation to calculate this. Right, now very similar to this, we have what is called as the angle of arrival. Sorry, can you repeat? I couldn't hear you. Huh, okay, okay. Only MCQ questions, is it? Huh, okay. So the plotting of the graphs might not come in that case, right? So in such cases, maybe calculation of any one part of this, like what is the angle of arrival, you can just calculate and enter the value, right? So part by part it might come. They will give an equation and they'll just ask you that what is the angle of arrival, what is the angle of departure, right? Or right, what are the angles of the asymptotes, or right, something, a part might come, not the whole thing. Okay. All right. So the equation for angle of arrival is very similar to the equation we wrote. Only the positions of poles and zeros get exchanged. So this is arrival is equal to, this is 180 degrees minus the summation of angles because of zeros. First we write this. From this we subtract summation of the phi of those. Alright, so like this we will calculate. So either we will be having angle of zeros to calculate, angle of arrival to calculate, or the angle of departure to calculate in a given place. Okay, and uh, okay, also we can find the range of k for stability. Already we have done that, so that might also get included with the question over here, right? So because k is unknown, we know that the k will not be given here in any question. So that means right? What range of k this system is stable can be asked, right? So what we do, we'll keep k as it is in the equation and we'll solve the RH root. We'll make a root table, right? From that itself we have to find what range of k, right? For what range of k the system is stable, we can answer. Okay, that's also possible. Anyway, we'll solve some problems based on this. So these are the steps to be followed to plot this. So once we solve everything, will be knowing that what is the exact shape of the curve to be plotted. All right. Okay. So this is a problem number one. Plot the root locus for the system having the g of s into h of s equals to k divided by, this is s into s plus 1 into s plus 2. So as soon as we see this, it's very clear that we have three poles, correct? So number of poles equal to 3. How many zeros you have? You don't have any zero, right? So the poles are positioned at different points, like P1 is equal to 0, P2 is equal to -1, and P3 is equal to -2. So according to the step number 1, right, which we already have seen, right, we identify the number of poles, the number of zeros, and we also identified the number of branches of root locus, which is maximum of this, right? So P is 3, Z is 0. So how many branches you are going to have? 3 branches. And out of those 3 branches, how many are going to infinity? It is the minus z, right? Or z minus p, its magnitude. So it is once again 3. We have 3 branches and all the 3 branches are going to infinity. That's what I come to know about this particular graph. So there are 3 branches, right? And all 3 branches go to infinity. So which also gives us some idea that how many asymptotes you need, correct? 3 branches going to infinity means I have to find 3 asymptotes. Okay, right. So as a first step, at the end of the first step, we have mentioned that you start drawing the graph. Okay, so I think this is how it looks like. Okay, now let's mark the poles and zeros. So there is a 0 over here. This is at 0, right? And maybe this is at -1 and this is -2, right? So this is the real, this is the imaginary of S. Okay, so what's the next step? Can you recall? Yes, so I can say that which part of the real axis we have root locus, right? So I come to know that this between 0 and 1 I have the graph, correct? And since both are coming towards each other, I am expecting a breakaway at a later stage. Also between -2 and minus 1 and -2 I don't have any, but -2 onwards till infinity I am expecting, right? So this is what I expect. Like this I can directly write to infinity, just goes towards infinity. All right, fine. So that's my next step, and I understand that. Okay, this is done. So what should be the next step? Okay, I can find a breakaway point. Normally, if you go in the order, I think the asymptotes will come first. Okay. So in order to find the asymptote, you need to calculate what is called as the centroid, right? So I'll write that now. So how many? I'll just make a point here, just uh, to note that. So how many number of asymptotes? So this is number of one goes to infinity, but there will be a asymptote supporting this. Okay, so any branch that goes to infinity will it actually needs an asymptote. So number of asymptotes, what's the equation you use? It's p minus z, right? The magnitude, correct? So that means it's 3 minus 0. So three asymptotes are there, which means first let's calculate the centroid. That is sigma asymptote is equal to, what is the equation? Equation says the summation of the poles minus summation of zeros divided by the p minus z, correct? So we see that summation of poles are located at different positions like 0 and at -1 and -2, and there is no 0, so I don't have to write anything after this, or simply it's a 0 whole divided by, this is 3, correct? So it's -1 -2 is -3 by 3, which is equal to -1. So at -1 I can actually keep updating the same graph. Okay, so at that point -1 I'll mark another point saying that this is the sigma a. Okay, at -1. Now from -1 I have to draw 3 lines. So how do you identify the orientation of the lines? By calculating the angle, right? Angle of asymptote. So angles of asymptotes, sigma, okay, not sigma, phi, right? Okay, so this is phi a. What is the equation? That is I think 2 odd number, so 2 cube plus 1 times 180 degrees all divided by the number of asymptotes, that is p minus z. Okay, so in this case the phi a will be equal to 2 cube plus 1 into 180 by 3, so this is 60, right? So 2 cube plus 1 into 60 degrees. So what are the values of q? Since I'm expecting only 3 graphs, 0, 1 and 2 you can put, right? So let's calculate. So what is phi a1? Q is equal to 0, so it is simply 60 degrees, correct? Next, phi a2, second asymptote, put q equal to 1. So 2 plus 1, 3 into 60, that is, and what should be the phi a3? That is 2 into 2, 4 plus 1, 5, 5 into 60, so that is 300, right? So I go back to the graph and we'll plot. So from this, making an angle of 60 degrees, you draw one asymptote. Okay, making an angle of 180, draw the second asymptote. Okay, and making an angle of 300, draw the third asymptote. Okay, so what we expect is we have to show the angles as well. So this is how. So this complete angle is 300. Okay, this angle is 180 degrees, and this angle, this is 60 degrees. So we have 3 different asymptotes. All right, next I have to asymptotes are done now. 3 asymptotes, angles of asymptotes also calculated, and we plotted asymptotes. Okay, now we can go for the breakaway, right? Okay, so to find breakaway, point, so we need to perform this dk by ds equals to 0, right? From where I am going to get, I will start with 1 plus gh equal to 0. So that is 1 plus the given equation. that is k divided by, because g into h is given, all right, s into s plus 1 into s plus 2 is equal to 0. Okay, from this, yeah, okay, I want you to calculate and tell me what is the equation of k that you are going to get. Okay, so that should be minus s into s plus 1 into s plus 2, right? Now I want you to perform the dk by ds for this. Calculate what is dk by ds. Okay, so that should be minus of, okay, plus 2. So when I say the dk by ds should be equal to 0, this implies, anyway, negative will go away. This is 3s square plus 6s plus 2 equals to 0. Now I need to solve this to get the values of s where the breakaway happens. Okay, so please find the values of s. Okay, one of the root is minus 0.4226 and 1.577. So I just verify which one is suitable for us. I'm expecting the value between 0 and minus 1, correct? So that means the first one, correct? That is minus 0.42, right? So select this, you neglect this, right? So therefore break away point is equal to minus 0.42. Okay, that's okay, absolutely fine. Now I understand from this graph saying that at a particular point, at a particular breakaway point, let me mark it, say here, this is 0.5, slightly before that, so maybe this is the breakaway point. Okay, this is a breakaway. I'll mark here, so 0.42, not visible, can you see now? Just a second, I'll share once again. You can see, right? So we've, let's say that this is the breakaway point 0.42. I can have, I can guess the shape now, right? I know that this has to start from 0.42. Both the branches will break away. It cannot cross the line which is already drawn. It cannot cross and go like this, right? It has to lie within the uh, within this region, right? It has to be within this region and it has to go to infinity. So since I'm, whatever I draw on the one side of the x-axis, same thing will be copied below. So I can guess that it actually starts like this and it will go to infinity. Okay, so same thing I can even draw below. Okay, so it has to be symmetric when we draw. Okay, I'll correct that. Okay, so I'll try to make it as symmetric as possible. So something like this, maybe. Okay, now I understand that I can find out where the, right, where it's going to cut the y-axis, correct? Recall the RH criteria, right? Recall the RH criteria where we actually found the range of k, and for a marginal stability case we could get the answer for, we could get the two values of s, right, where it cuts the imaginary axis, right? This is for giving more specifications about this particular root locus. We can do that, right? So actually that is included, that has to be included when I get these kind of situations. Okay, so let's find that now. So how do we find that? We can find the equation 1 plus gh equal to 0. Correct? First we'll write that. This is to find the intersection with imaginary axis or y-axis. To find the intersection with y-axis, what we have to do, RH criterion needs to be applied to 1 plus gh equal to 0. Okay, when I say 1 plus gh equal to 0, this is 1 plus k over s into s plus 1 into s plus 2 equals to 0. Okay, what is this equation? Can you simplify? Yeah, what's that? I think s, okay, 3s square. All right. I think that's the equation for dk by ds, right? I think we get a s cube now because you see the, right? Okay. So this is s cube 3s squared plus 2s plus k, isn't it? Equals to 0. Anyway, the denominator will go away, right? This is the equation. For this, you need to draw the RH, right? So start with the table s cube, s squared, s to the 1 and s to the 0. So this is 1, 3, 2, k and 0. Okay, so please fill the table. 6 minus k divided by 3. This is 0 and this is 0. Okay, it's k 0 0. So from this I understand that since the first two entries of the first column are positive, I am expecting the other two terms containing k also to be positive. So the last number is k, it should be definitely greater than 0. Okay, the second term says that 6 minus k should be greater than 0, so k should be less than 6. So k is less than 6. So we understand that this particular system is stable if 0 less than k less than 6, right? So I need the marginal value, that is this. At 6, this is marginal. So what I can do, I can write an equation in terms of with the value of 6 as k for the term containing s square. That particular row you take up from the table and put the value of k as 6 and write an equation. So what is that equation? Equation is 3s square plus 6 equal to 0. Are you okay? Right. Now you solve for s. Plus or minus root 2j. So plus or minus j 1.41 something. Okay. So that means this is plus j 1.41. The other one is minus j 1.41. So this is the root locus of the given question. Everything we needed to find, we found and we have plotted. Okay. Right. So that's the answer, and there is no question of finding out the what you call Angle of departure, angle of arrival will not come into picture because there are no complex poles or zeros. Okay, only for complex poles or zeros we have that part.